Now we're going to transition to the next speaker. Next, we have Svitlana Volkova, who is also the Chief of AI at Aptima Inc. And she's also the former Chief Scientist at Pacific Northwest National Laboratory. So thank you very much for joining us today. I'll let you take it away. Thank you.
Thank you. I want to make sure you hear me and can see my slides.
Yes.
Awesome. It's great to be here, and it's great to speak after Emily, who covered a lot of the challenges in AI test and evaluation that actually we have been working on together. And I want to focus more on the human AI ecosystem, the way that we develop these models, frontier models, and agentic AI workflows, as well as we evaluate these workflows in operational setting. Primarily, I want to discuss how we have been integrating AI and specifically agentic AI and compound AI systems that is scientifically productive and operationally effective and grounded in human-centered design and engineering. And this is essential for adoption by major and mid-scale facilities. There are three key components. One would be what I call compound AI systems. So these are not only agents, these are not only frontier models. It's some kind of a combination that we usually deploy to the Department of War that include access to frontier models. They have specialized agents and they have agents aligned with data, so using supervised fine-tuning or reinforcement learning or retrieval augmented generation. This could be used to accelerate cross-disciplinary research and discovery. The second component is automated research workflows that enable scientists to focus on innovation while agents are doing a lot of the data integration, experiment generation, and validation. And finally, a very important component, the human AI teaming that creates trusted partnership where AI augments human expertise and is seamlessly integrated into the automated workflows. So let's start with scientific discovery. There have been some prominent papers developed over the last, I would say, 4 years, and it started with using frontier models back then, GPT-2, right? And we pre-trained these frontier models from scratch for specific domains like chemistry or material science or biology. And then we moved from the era of frontier models and using them for scientific discovery to the era of agents. So there have been the AI scientist and the agent laboratory from Hopkins, as well as the Cosmos model that was recently released. So imagine you have agents that are trying to help scientists to make scientific discoveries. So all of the spaces has been studied extensively. And interestingly, from industry, there have been made significant progress in the last year, where the Future House, they basically released and published on agents like Owl and Falcon that can automatically, agents go and do scientific discovery and they validated it in the lab. And also Google released the AI co-scientist. But all of this progress is great, but there are still requirements that are missing. And I call it compound AI requirements. So first of all, research is fundamentally multidisciplinary. And primarily when we develop these agents or frontier models for science, we focus on one discipline. So this aspect is missing. When we interact with these models, we're missing the multi-turn human AI interaction. And then we primarily focus on a single agent, right, to do X or do Y, rather than having an integrated multi-agent system that works seamlessly with the scientist. Multimodality is still a very understudied aspect. There have been models that are multimodal that take images and tables, but how about instrument data? How about data from the large facilities? And all of this integration is still a challenge. And most importantly, what Emily mentioned, the benchmarks, right? So especially benchmarks that are not domain specific, but they are cross-disciplinary and they are cross-modal. And moving beyond benchmarks, we really need to evaluate these compound AI frameworks for scientific discovery using the human agent environment interaction workflows, right? So the workflow evaluation rather than benchmarking. And that's what we have been working on. This work has been funded by DARPA and Oscar, where we developed a system, it's called BiasH, that focuses on human agent workflow. So we start with the human-centered design and we ask scientists, what do you want to do? And they want to do summarization, or they want to do debating, or they want to do brainstorming. So these are the three initial workflows we started designing, and then we kind of developed the agentic system under the hood that is focusing to satisfying these user needs and requirements. And on the right hand side, you see the example interaction where the scientist is asking a question, system returns the answers, and then there is this multi-term interaction across agents, multiple agents, and potentially multiple scientists. And I want to show you a demo. I'm going to click through it, but I want to give you an idea how a scientist will interact with a system, asking a question like with a regular chat, you can imagine, and that the system returns an answer, but the way that the answer is derived, it's actually retrieving across domains, and it's pointing scientists which domain the answer was found. And it also gives evidence where the answer was found. It provides visual evidence and also text evidence, as you see in the table, right? So you see the domain, you see the link to the paper, the extracted information from the paper, and the evidence. And the next step, after you can refine your query, you can further interact with the system, but then later you would like to reason about this answer, right? So basically you generate another query, and then you ask the reasoning agent, go and find contradictory evidence versus supportive evidence. In addition to that, what you can do, you can also call tools and go and search on the web in case that in your internal database the answer wasn't found. So let me quickly move to the reasoning part, right? So the reasoning part, you're trying to find supportive and contradictory evidence. And what's important, when the reasoning sub-agent components are interacting under the hood, you can get a score, you can get an empirical quantitative result, whether the evidence that you collected either on the web or within your database is supporting or kind of converging with your answer or diverging from your initial hypothesis. So that's the system at glance. And let me show you how we build it. So as I said, there are multiple domains. We're using, in this case, retrieval augmented generation and agentic workflows, multiple agents. We have a query planning agent, a response synthesis, reasoning agent, retrieval and translator agent. Agents are not LLMs. Agents, they have memory representations. They remember what they ask. They store the evidence they collect and the evidence of interactions. They interact with the user, and they also interact among themselves, and we establish certain behaviors and profiles for different agents. As you can imagine, a reasoning agent will have a different profile behavior compared to a retrieval agent. And here I'm showing you the kind of the technical implementations, how we did it was the vector database. We're using pedantic AI for agent interaction, transformer embeddings, and tool cooling for query planning. So this is kind of the backend architecture of what we call a compound AI system that consists of frontier models, agents, and tool calling. We tested the system across multiple disciplines. So we collected over 500,000 papers from public databases, and we ingested it and we parsed them. So we basically parsed the PDFs, visual content separately, tabular versus text, right? So we can retrieve across these different modalities. And the way that the retrieval agent works, it starts with the query planning, right? So it takes the query and it doesn't simply match it like using an embedding space with the potential papers. Instead, it chunks it and it plans what aspects of the query, which specific domain agent to ask, right? So that's what we call an in-domain evidence gathering, search and summarize relevant information to the query from each domain. And then we kind of get the background expertise retrieval from these different single domain agents, and we synthesize the answer in the end. So that's how the retrieval works. And reasoning is slightly more complicated. We distinguish two types of reasoning: macro reasoning and micro reasoning. And we basically, from the reasoning agent, go and collect evidence across domains in these different kind of focusing on different, whether high level evidence versus more micro level details. And then what we do, we kind of sync it together and do this, what we call metacognitive optimization, which is another self-reflection that the reasoning agent has to have the second thought and then kind of iterate on the evidence collected given the query. Okay, and with all of that in the back end, how do we evaluate when we and since this is the first system that is cross-domain, we really didn't find any benchmarks that are cross domains, but we played with a few that were publicly available, and they are reflecting other system performance developed by industry and academia for scientific discovery. We tested GPT-4o and Llama 3 models, and here you see on this plot for LitQA version 2 evaluation, which is from 2024, which seems a long time ago right now. We compare vanilla models versus vanilla with retrieval augmented generation and our retrieval agents. And then you see for both models, agents outperforming RAG. And then another benchmark, which is WMDP benchmark, we also see that retrieval agents are outperforming vanilla models and retrieval augmented generation. Then for other benchmarks, one humanity last exam bio subset is a very challenging benchmark. You see accuracies are like below 10%, which significantly improved, by the way, since the benchmark was released last year. But you see not necessarily retrieval agent is outperforming retrieval augmented generation. So we see for Llama models that are much smaller model than the GPT-4o, we see RAG improving accuracy significantly. And the last benchmark is the very famous one, GPQA, which we suspect exists in the actual frontier model. So we assume the GPT-4o read the GPTQA from the web. So it has it, it knows it. That's why we see this huge performance for the vanilla model when we use the GPT-4o model. And this is all benchmarking. Treat these numbers with the grain of salt, because the actual evaluation has to come into how the models are used within the workflows for the scientists, right? And that's the next steps that we are working on. In addition to the existing benchmarks, as I said, there are no cross-disciplinary benchmarks. So we decided to develop our own cross-disciplinary benchmark. We focused on biology and artificial intelligence. And we created 100 cross-disciplinary question-answer pairs, and we compared the models. As you see here, we basically plot delta of how different models outperform compared to the vanilla benchmark. And you see a lot of green, except of a few cases for like GPT-4o or 5.4 that the performance was degraded. But this is a public benchmark that we are releasing and that will be available. If you're interested, reach out. And that's, again, it's for AI and biology. Beyond benchmarking evaluation, what we also did, we also looked into causal evaluation of system behaviors. The design choices that we make, the data, the questions that are present in the data, whether we're using the agent or we're using just simple retrieval augmented generation or other design choices, tool calling, web search, you name it, it all affects how the system performs. And in order to really test it, we need to understand when I turn this knob and I make this design choice decision, how it's going to affect my generation quality. And that's what we did was the causal evaluation. You see here the heat map, where we see different interventions. Interventions could include the data because all of these questions are different, the benchmarks are different. You see whether the agent was present or not, or RAG was present or not, versus a different type of model. And then you kind of see the negative and positive effect from the causal modeling. And we use multiple types of causal models, structure equation models and treatment effect estimation. And we look into the quality of the generation as an outcome, structure, readability, and quantity. So how long are the answers, and then whether they are readable by the human. And you see how the space is actually really like different. And you see, for example, that for GPQA, readability of the generation has really negative effect, similarly across all of the other design choices. And causal analysis in the end, causal analysis of model behavior allows you to really understand what is effective your generations or predictions. Okay, and then if we move to a more complex evaluation, which is a human AI evaluation, the way that a recent paper, Cosmos paper, looks at it, it basically says we do not try to replace the scientists, we try to augment it. But the way that they're augmenting it is like, oh, we give the data, the scientist gives the data to AI, AI does everything, and then the scientist looked at the end, right? That's not sufficient. But I'm trying to show here that we really need to integrate AI, automation, scientist interaction. It could be multi-turn all over, like it happens in the natural world, right? When we analyze the data, collect the data, and interact with the data as scientists. So that's what we are trying to do with the human agent research workflow evaluation. And for that, I want to talk briefly about the another DARPA effort, which concretely focuses on human AI evaluation. It's called MHAT, Empirical Models of Human AI Teaming. And what we've done here, we basically take small amount of interaction of, in this case, we didn't have scientists, but I'm trying to present it to you as an example for this application. Imagine you have a small amount of data, real world data, scientists interacting with data, instruments, agents, AI, and then you take that small amount of data and you simulate at scale. And you simulate with interventions. You can simulate human digital twins and their vulnerabilities. You can also simulate agents and databases and tools and instruments and their vulnerabilities. And all of that is supported by our memory representations, and we're using, if we want to align our data to the model, we're using fine-tuning or agentic context engineering these days, and use causal models to evaluate the results of the simulation. So that's kind of the overall big picture, how we're evaluating human AI teaming. And what we can do, we can test interventions. And in our previous scenarios that are more DOW focused, we tested human propensity to trust, different personality profiles, competency levels, and so on. For the AI manipulations, you can test reliability of the agent, transparency, whether if the agent is lying to you or not, what type of the model is used. And there are some other types of interventions that are more complex that include teamwork and task work and environment manipulations. So this is another dashboard, another demo I wanted to show you where we simulated, that again, that's a DOW scenario where we simulated search and rescue operation in a synthetic environment, but we run a lot of human AI modeling experiments. And this framework allows you to do statistical analysis and look into how different interventions, for example, agent reliability affects the teaming performance, right? So team coordination, team communication, and other different dimensions. So let me maybe scroll you here. So basically that's, if I pause here, these are different types, different dimensions, team processes, team communications, and different trust dimensions of human AI teaming. And you can do statistical analysis and see what affects what. In addition to that, we have LLMs and agents under the hood here, and then you can design your analysis from different perspectives. You can brainstorm with your agents, you can summarize the results or get the insights that you want. And this is all available. Demo is available on this link.
2 minutes left.
Yes. Okay, so a few more slides. Let me maybe jump here. It's good that we can test using the benchmarks. They are not perfect, absolutely, we all know that. And we are moving away from the benchmarks to more workflow evaluation and human AI teaming workflow evaluation. But our current DARPA effort is focusing on safety of these workflows and interactions. What I showed you is that the ability to test how humans are interacting with agents, but there are three critical dimensions here. Agents are also interacting with the environments, and agents can go rogue. And humans are interacting with the environments. They're interacting with instruments, interacting with databases, and this can go terribly wrong. So we are designing a taxonomy, a framework to investigate and empirically test intended and unintended agent behaviors and human behaviors within this interaction space. So in order to do that, I think in order to transform research workflows, we really need to make sure that we integrating scientists and humans and automation and autonomy in the scientific research workflows, and we building trusted human AI partnerships, which will help us to really achieve cross-disciplinary discovery, which is needed to really enable the breakthroughs that emerge in the cross-disciplinary boundaries. So this is my last slide. I want to thank the team, and if you have any questions, my information is here, and I would be happy to release the slides and share the demos and more details. There are some papers that we recently published that are also publicly available. Thank you so much.
This is great. Thank you, Svitlana. This is wonderful, and thank you for the bibliography as well. We will get you a PowerPoint and post them online. Encourage people to follow up with you with questions and look up your papers. So please join me in thanking Svitlana for a wonderful presentation. Thank you.
Thank you.
If I can have just a quick comment, great to see you, Svitlana. But also, I really like that the last couple of slides that last slides that you showed were thinking about how these agents, different kind of failure modes at the reasoning level or
Exactly.
level. We're looking at other projects also at mechanical failures, so cyber infrastructure failures, and how that affects also agent behavior. So I'm glad to see the different aspects that we're considering. So that's great.
Awesome. Thank you.